last lecture we were discussing this result. The closedness does not imply the boundedness of a linear operator, and conversely the boundedness does not imply the closeness. So, first part of this result we have already shown by an example where the operator is closed, but not bounded, and as an example we have taken a differential operator from C01 to C01, and in that case we have shown that operator is not bounded because of a particular function. If we take x n t to be t to the power n, then this is unbounded operator as we have already discussed, and this operator however, it is closed operator, is it not. So, that operator is closed we have seen, and for unboundedness here we can say unbounded operator, because if I take x n t to be t to the power n, t lying between 0 and 1, then the derivative t x n becomes n t n minus 1, and the norm of t x t is equal to say n, say n. So, norm of t x x n is greater than equal to n times norm of x, is it not, but norm of x n is 1. So, we cannot find a c, we cannot find c such that it always be less than equal to n, means this condition less than equal to this does not hold good. Okay. So, this part we had said unbounded operator. Now, the second part of this, that boundedness does not imply closeness, does not imply closeness. Okay. And the example is, let us take an operator t from dt to y, which is dt to dt, which is subset of x, and this operator be a identity operator, be an identity operator, that is an operator which transfer x to x. Okay. Identity operator. So, it is a transform x to x. So, obviously, this identity operator t is linear, is it not? There is nothing to prove for it, linear, as well as is a bounded operator, because norm of t x equal to norm of x. So, it is a bounded with the norm 1. Okay. So, it is a linear and bounded operator, but t is not closed. Why? This we are choosing as dt is a proper subset. This is a proper subset. It means the range set is a proper subset of x. So, if I pick up, if we take a point x belongs to x minus dt. This is our x and here is dt. I am picking up a point x outside of dt. Okay. Now, this if it is t is closed, then graph of t must be, that is what we get it is x n converges to x, t x n converges to y, if is it not, and then y is equal to t x, that is what we get it. So, if we take a sequence x n, then this follows. Okay. So, if we take sequence x n in dt, then if we take a sequence x n in dt which converges to x. Okay. it means all the limit point of the this does not belongs to this. So, if we take a sequence x n, image is T x n, that T x n will not go to T by, is it not? By is equal to T x will not be there. So, it is not. So, by is not equal to T x. Is it clear not? Where by? Therefore, this operator T is not closed. So, the operator is bounded, but is not. So, it means we cannot have a relation between the closedness and boundedness, but under a certain restriction we get the relation. Okay. So, that restriction we will see in the afterward. In fact, the lemma which shows is like this. There is one result. The result is, let T from domain dt to y be a bounded linear operator. Bounded linear operator with domain dt which is subset of x, where x and y are norm spaces. Norm spaces. Okay. These are the norm spaces. Then if dt is closed, dt is closed subset of x, dt is closed subset of x, then T is closed. T is closed. Means this condition is dt must be a closed subset of x. All of its limit point must belongs to dt. Okay. Then only the T will be closed set. Okay. Second result says, if T is closed and y is complete, y is complete, then the domain dt is a closed subset of x. Closed subset of x. Okay. Now, proof of this, it means this gives the condition under which the T will be a closed operator. The condition is sufficient condition, if dt is closed then T will be, and conversely if T is closed and y is complete, then our domain dt will be a closed subset of this. Okay. And y should be a complete unity. Okay. That is what. So, let us see the proof further. What we want is that T is closed. So, let us take a point in the closure of that T is closed means x n converges to x, and if T x n converges, the T x n converges to y, then y is equal to T x. Okay. So, that is what we wanted to show. So, let if x n is in dt, if x n belongs to dt and such that x n converges to x, okay, and such that T x n also converges, this sequence T x n also converges. Okay. That is what. Now, if T x n converges, then converges to some point, then y is equal to T x. That is what we wanted to show. Okay. Then x. Now, since dt is closed, x n is a convergence sequence converging to x. So, x is the limit point of the sequence x n. So, x must be belongs to the closure of dt. Okay. So, clearly x belongs to dt closure, which is the same as dt, because dt is closed. Is it not? So, that is not is it. Now, T x n converges. Okay. Now, what is given is T be a bounded linear operator. So, since T is a bounded linear operator and the linearity and the continuity are the same thing. Sorry, if a linear operator, then boundedness and continuity are the same. So, since T is a bounded linear operator, therefore, since T is bounded linear operator, so it will imply T is continuous, is it not? So, since T is continuous, so we get from here that it will transfer the convergence sequence to convergence sequence. So, x n converges to x implies T x n will go to T x because of the continuity, because T is continuous. Okay. T x n converges is already given, so it will converge to T x. Okay. Now, T x is a point in dt. So, image of this will be the in the domain in the range of t. So, there will be a point y where the T x n will go to t. Okay. So, this shows that by T x belongs to dt. T x is in the range set, therefore, T is closed. Is it okay or not? By definition, by definition. So, this the proof. Okay. Second part, B part proof. What we want to show, if T is closed and Y is complete, then domain is a closed subset of X. Okay. So, let us take all the limit points of the domain all the limit point of the sequence in dt must be in dt. So, let X be a point belonging to the closure of T. If I prove that X belongs to dt, then dt will be closed. Okay. Now, since X belongs to the closure of this, so by definition, by there must be a sequence x n in dt which converges to X. Okay. So, there is a sequence x n in dt such that x n converges to X, because X is the limit point of this. Okay. Now, further T is given to be bounded, T is given to be bounded, is it not? So, by definition of the boundedness, norm of T x n minus T x m, this is equal to norm of T x n minus x m, because T is linear, is it not? And again T is bounded. So, this is less than equal to norm of T into norm of x n minus x m, because T is bounded. Is it okay? T is bounded. Fine. Okay. So, this will be now x n is a sequence which is convergent, is it not? So, what you say is that every convergent sequence is Cauchy. So, this will be a Cauchy sequence, therefore, this has to be Cauchy. So, this implies the sequence T x n is a Cauchy sequence in Y, but Y is complete. It is given, this is given. So, every Cauchy sequence must be convergent. So, T x n, this sequence converges to say Y belonging to Y, okay, because Y is complete. Okay. Now, given that since T is closed, this is given, and X is an element of the domain dt. So, by the definition of the closeness, if T x n converges, then the limit point T x must be equal to Y. So, by definition T x must be Y. Okay? Clear? Hence by is closed and dt is closed. Hence dt is closed because x belongs to dt was arbitrary. Because x is an arbitrary point of dt closure. Because if we take any arbitrary point, correspondingly we can always find the by in this such that T x equal to y. Okay? So, this shows that dt is closed, x must be in dt, is it not? This because of this closeness. Okay? So, this completes the proof of this. Okay. So, this portion in fact, we the left out portion of the last lecture. Now, we will take up the few application of the Hahn-Banach theorem, where the Hahn-Banach theorems are used. In one of these topic which we require is the adjoint operator. The theory of the adjoint operator and their corresponding results and the properties requires that Hahn-Banach theorem very rigorously. Okay. So, let us see the new topic which we wanted to discuss is the adjoint operator in general from one norm space to another norm space, and then let us see what is the relation between the adjoint operator and the Hilbert adjoint operator and how this can be represented in terms of the matrix, because every linear operator, every operator defined on a finite dimensional space can be represented by means of a matrix. So, correspondingly the adjoint operator, what should be the form of the matrix if T is a adjoint operator. Okay. So, these things we will discuss in. So, let us see that adjoint operator. Okay. Let T be a bounded linear operator from one norm space x to the another norm space y, where x and y are norm spaces. Okay. Let us, we wanted to define the adjoint operator of this. Okay. So, let us pick up a bounded linear functional g on y. Let x dash and y dash be the dual space of x and y respectively. Dual means set of all bounded linear functional. Dual means set of all bounded linear functional, is it not? Bounded linear functional. Okay. These are the set of all bounded linear functionals are the duals. Okay. This is, so let us pick up a point, let G be a bounded linear functional, G be a bounded linear functional defined on y, that is G is a point in y dash, bounded linear functional. Okay. So, since G is a bounded linear functional on y, it means, so G will be defined, G is defined for all y belonging to capital Y, because it is a linear functional defined on y. Okay. So, it is a bounded. Let us take, let us define or let us take y is equal to T x for some x belonging to capital X, because this is our x, this is y. So, if we take any x here, okay, T is a bounded linear operator from x to y. So, it will transform the image of x under T as T x. By dash is this set of all bounded linear functional defined on by, is it not? This is by dash. It means this is our G. G is an element of this. Domain of G will be T x. Domain of G will be T x. That is, G is a by to R. G will be by to R. Domain will be by, that is all T x. So, G is defined for all by, which is T x. Say, okay. So, now let us take start with x, then corresponding to x we wanted to define a bounded linear functional on x dash. Okay. Take x, because domain of this will be from x to R. So, fix x, then we wanted to define f of x in terms of G. So, how to define this is, we are taking f, once you take x, then you are taking T x here, okay, and T x is G of x is a real number. So, we can define, let us define a functional f on x as f of x equal to G of T x, because it is a function, means it is a real valued. So, what I am taking is x belongs to capital X, we are taking the f of x a real values, but this value is defined in terms of G and T, because T x is a point in y, G is a functional, a bounded linear function defined on y. So, G of T x will be a real quantity. So, I am defining f of x equal to G. So, it is a functional. We claim that f is linear, and bounded.
Sir, our requirement is that we are taking two functional f and g. Only the point is that value should be the.
No, we are taking G as a bounded linear functional in y. We wanted to relate this G with a bounded linear functional on x. So, that is why we are wanted to introduce a functional f, which is a bounded linear functional on x. So, corresponding to G we can get the f and vice versa also. Okay. That is the rest. So, that way we can define the operator from y dash to x dash, and which is nothing but a adjoint operator. So, that is okay. So, this f which we have defined, we claim this is a linear and bounded functional on x. Why? Because because f is linear, since G and T are linear. G is a bounded linear functional on y, T is a bounded linear operator from x to y. So, composition of the two linear functional will be linear. So, f will be linear. F is bounded because mod of f x, this is nothing but the mod of G T x, but G is giving to be a bounded linear functional. So, by definition this is less than equal to norm of G into norm of T x, as G is bounded linear functional, okay, functional on this. Further, T is a bounded linear operator. So, it will be equal to norm G, norm T into norm of x, as T is bounded. Okay. So, we get the mod of f x is less than equal to normal. This is true for all x belonging to dt, belonging to x, sorry, belonging to. So, we can from here we say mod of f x over norm x, take the supremum over all x belonging to capital X, x is not equal to 0, is less than equal to norm g norm t, but this is equal to norm f. Okay. So, this implies that norm f is less than equal to norm g into norm t. So, this f is bounded, f is, therefore, f is bounded. Is it okay? So, we have shown that f is bounded. It means, if we start with a bounded linear operator from by, then one can associate an bounded linear bounded linear functional in by on by, then we can take associate a bounded linear functional on x. Okay. Now, this reads the concept of the adjoint operator. Okay. So, now let us define the adjoint operator. Is it clear or not? So, define adjoint operator. Let T from x to y, T from x to y be a bounded linear operator. Let be a bounded linear operator. Let T be a bounded linear operator where x and y are norm spaces. X and y are norm spaces. Clear? Then the adjoint operator T cross, the adjoint operator denoted as T cross, denoted by T cross, is an operator from y dash to x dash. They denote the dual spaces. Okay, dual spaces x to y is defined by f of x T cross g x equal to g of t x, where x and y are the dual spaces of x and y respectively. Okay, this. So, the adjoint operator T cross defined from y dash to x dash as T cross g, g is an element of y dash, T cross g of x, image of this is the g of t x. Clear? It means x you are choosing from capital X. So, this is a functional, this is a real valued thing. So, this we are taking a f of x. Is it okay now? So, we are defining where x dash and y dash are the dual spaces of x and y respectively. Is it clear now?
So here the small f and small g are as usual as previous.
Small f, small g are the bounded linear functional. Okay. So, what we are doing is we are just picking up the x, this is our x, this one is y. Okay. Okay. Then what we are doing is this is our y dash and here is x dash. Okay. So, we are taking x here, then it is giving to be the T x. So, T x here. Okay. Then this is from by to by dash is G. This is our G, is an element belonging to G. So, whose domain is by. So, G of T x we are taking to be the x dash. This is our F. Okay. So, relation between G and F is given by this, and this operator T cross which relates G to F, is it not? Relates G to F is nothing but the adjoint operator. So, an adjoint operator is an operator from by dash to x dash such that T cross G of x is equal to G of T x or equal to F x. Okay. Is it clear? So, corresponding to each G we can find F here, and vice versa also one can. Okay. Now, this operator T cross which we have got it is also a bounded linear operator, and the norm of T cross and norm of T will be the same. Okay. Because if they differ then it will no use. Okay. So, let us see the next result. Norm of the adjoint operator. The adjoint operator T cross as defined above, is linear and bounded and have the same norm as the norm of T. That is the one we wanted to show. Is it okay? The proof of this. The operate T cross is linear. Let us see first. How this? T cross, the domain of T cross is G, sorry, is by dash, is it not? T cross is defined on from by dash to the. So, domain of this T cross is y dash. So, let us pick up the point G 1 and G 2 in by dash. Let G 1 and G 2 are the two bounded linear functional defined on by belongs to by dash. Consider T cross alpha G 1 plus beta G 2. If I prove this is alpha time T cross G 1, beta time T cross G 2. Okay. Now, this is a composition of the two functional. So, image of this under X. Now, by definition T cross G x, this is that T cross G x is G of T x. So, by definition this will be equal to alpha G 1 beta G 2 x, is it not, beta of T x, G of T x. Now, separate out. So, alpha G 1 T x plus beta G 2 T x, is it not. Now, this will be equal to what? Alpha T cross G 1 x, because this can be written like this, plus beta T cross G 2 x. So, x can be taken common and we are getting this. So, T is linear, is it not? Therefore, T is linear. So, T is it okay or not? Sorry, T cross is linear, not T. T cross is linear, because T cross is. Now, we wanted T cross to be bounded, T cross to be bounded. Okay. Now, let us take this T cross G. T cross G. Now, T cross G is nothing but what? F, is it not? T cross G is nothing but F, and F we have proved one result, that is norm of F, yes, this will be equal to norm of F equal to norm of G into T. हाँ, where it is? हाँ, this will be F T x, and then this is the norm of F equal to norm of.
सर आपके हाथ में जितना स्लाइड है वो रखो और जो नहीं है उसमें वो कुछ नहीं।
इसमें
सर इसमें
इसमें
वो जो आपके हाथ में नहीं है।
ये
सर ये तीन हटा दो। हाँ अभी जो स्लाइड में।
अच्छा इसी में। Okay, so norm of F, yes, this is over there. This one is there. So norm of F is less than or equal to norm of G. Okay. So using this thing, we can write this is less than or equal to norm of G into norm of T. Okay. Now divide by norm of G. So what we get from here is supremum of T cross G over norm of G, and G is belongs to what? Y dash, and G is not equal to 0, and that will be less than or equal to norm T. Therefore, norm of T cross is less than or equal to norm of T, is it not? So, this shows that T cross is a bounded operator. Okay? Norm T is a. Now, we wanted to show that norm of T cross is the same as norm of T. This is wanted to show. Okay? It means required to prove is norm of T cross is greater than or equal to norm of T, because it is already shown this. Okay? Now, this we will show. Now, here we will make use of the Hahn-Banach theorem. This is our x, this is say x, and then this is y. T is a bounded linear operator from A. So, let us fix up the x naught here, choose x naught, fix. Okay? Then corresponding this we get the T x naught. If x naught is not equal to 0, then T x naught will also not be equal to 0. Okay? Now, if we pick up a point x naught in x, then there will be a bounded linear functional f such that f of x naught will be norm of x naught and norm of f will be 1 by Hahn-Banach theorem. So, let us take x naught fixed. It means you are choosing the T x naught as an element in y. So, by the Hahn-Banach theorem, so what we get is, so Hahn-Banach theorem implies that by the Hahn-Banach theorem we can say that for every non-zero x naught belonging to capital X, there is a bounded linear functional G naught in y dash such that norm of G naught is 1 and the value of this T x naught under G naught will be norm of T x naught. Is it okay or not? Because basically this x naught will give the T x naught. So, now applying the Hahn-Banach theorem for T x naught. So, picked up a T x naught in by non-zero T x naught, there will be a bounded linear functional on by whose norm will be 1 and image of this T x naught under G naught will be the norm of T x naught. This is by the Hahn-Banach theorem. So, we get this one. Hence, therefore, G naught T x naught by definition G of T naught means that T cross G naught x naught, is it not the way in which we have defined? Okay. Then this will be equal to, by definition of the operator, this G naught T x naught, but G naught T x naught and is nothing but the what? F naught x naught, which is the same as F naught F naught x naught. Is it okay? Now, consider. So, writing this where F naught means T cross G naught, is it not? This is this I am taking a F naught. Okay. Now, consider norm of T x naught. By definite norm of T x naught is G naught T x naught. So, this is G naught T x naught and G naught T x naught is nothing but the F naught x naught because of this. Okay. And then F naught is given what? It is a bounded linear functional. So, it is less than equal to norm of F naught into norm of x naught as F is bounded linear, F naught is bounded linear functional. Okay. So, we are getting, but F naught is nothing but T cross G naught. So, this is equal to norm of T cross G naught, norm of x naught, but T cross G naught that can be written as, because T cross is bounded already we have shown. So, this will be less than equal to norm of T cross G naught into norm of T cross norm of this into norm of this. I will take another norm of T cross norm of T cross, this is less than equal to norm of G naught into norm of x naught as T cross is bounded. Already proved earlier, T cross is a bounded linear operator, linear functional, is it not? So, T cross is bounded. So, we are getting this. Now, from here we can say since norm of G naught is 1. So, this is equal to norm of T cross, sorry, it is cross into norm of x naught, and this right hand side was T of a norm of T x naught. This is less than equal to, let it be A. Okay. But we know, but T is a bounded linear operator, from x to y, from x to y. Therefore, there exists a C. Therefore, there exists a C such that norm of T x is less than equal to C times norm x, and the minimum value of C is norm T. Is it not? Now, if we look the A and B simultaneously, then norm of T x naught is less than equal to this, norm of T x is less than equal where minimum value is norm T. It means, what will be the relation between T cross and T? The T cross cannot be less than norm of T, because norm of T is the minimum value of C. So, A and B implies that norm of T cross will always exceed by norm of T, is it not? Therefore, combining these two, we get combining earlier we get norm of T cross is the same as norm of T.
Sir, because of means V is for any x.
Which one?
Means our relation V
Huh?
means Tx less than equal to C norm.
For any x.
For any x.
So, x is particular.
And A is for a particular x naught.
A is particular x naught, but even that this constant cannot be exceeded by the norm of T. Cannot be less than norm of T. It may be greater than or equal to norm of T. So, that is why it is going to be this. Okay. So, we get from here is that norm of T x naught is less than equal to norm of T. Is it clear or not? Therefore, this proves the theorem. Okay. Now, let us choose the example where this adjoint operator, how the adjoint operator can be represented by means of a matrix. Okay. Just like every linear operator T in a finite dimensional space, we can represent by a means of matrix. Here we will show that T cross, which is an adjoint operator of T, will also be represented by a matrix, and in fact, it will be the transpose of the matrix obtained by T. Okay. So, let us take an example here. Okay. The representation of, let us take the new page. Okay. Representation of T cross in terms of the matrix. Huh? Matrix. Is it okay? So, let us suppose T, let T be a bounded linear operator from Rn to Rn, be a bounded linear operator from Rn to Rn. Is it okay? T be a bounded linear operator from Rn to Rn, and since this is a finite dimensional, so it can be represented by means of a matrix, by means of a matrix. Okay. We are such a matrix by means of a matrix T E, which is say tau of j k, which depends, okay, where such matrix, such a matrix T E tau of j k depends on the choice of, depend on the choice of a basis E, E1, E2, En for Rn, whose elements are arranged in a definite order, in some order which is fixed, or in a definite order which is fixed. Okay? That is what means. The very clear, whenever we want the linear operator, representation of the linear operator in terms of the matrix, then first we have to fix up the base. Okay. Order of the element of the basis is fixed, because a vector space can have so many bases, is it not? So, let us fix up the basis. First element will be E1, second element E2 and En. Once you fix up the basis element, then a linear transformation will give you a matrix, and that matrix will totally depend on this basis. If you change the basis, the corresponding the transformation will give the another matrix like this. Okay. So, let us fix up the here the basis element. Oh, and this basis element is chosen with respect to x and y coordinate. So, let us fix the basis E as E1 E2 En as E1 E2 En with regard to x as column vector xi1 xi2 xin and by as eta 1 eta 2 eta n as column vectors as column vectors. Okay. So, let x and y are the column vectors in there, and then with the help of this you fix up the basis E, so that the T E will be fixed, will have a unique representation here. Okay. Then then y of y will be equal to T E x, and in component form where what is T? T is tau j k. So, where the eta j is the component sigma tau j k xi k, k is 1 to n, is it not? Okay. Now, let us take a set F, F1, F2, Fn be the dual basis of E, dual basis of E. In fact, this is the basis, this is a basis for Rn dual. Dual basis we have discussed. Okay. So, Rn where f j x k is the canonical delta, E j is the canonical delta. Okay. So, this. So, it means let f belongs to or G belongs to Rn dual has a representation as alpha 1 f1, alpha 2 f2, alpha n fn, every element. In fact, this is true for every G belongs to A, we have a representation like this. Okay. Then dual basis of this, and here what is a here f j by means f j by is what? By is an element in Rn, is it not? So, Rn means it is of the form sigma eta j or eta k E k, k is 1 to n, and now this will be f j E k will be 0 when j is different from k, and otherwise it is 1. So, basically you are getting eta j. Okay. So, we are getting this one. Now, from here we can say, so this one, therefore, we obtained is G y is equal to G of T E x, which is equal to sigma j equal to 1 to n alpha j eta j, because y is an element which is alpha j eta k. Eta j you can write in this form. So, you can write sigma j. Which expression? This one, k equal to 1 to n. No, k. Okay. This j alpha j, and now tau of j k x j k. Thus summation. This is the double summation k is equal to 1 to n. Now, this you interchange the summation. Okay. So, this we can write it as sigma k equal to 1 to n beta k x I k, where beta k is summation j equal to 1 to n tau j k x I k. Now, this will represents our matrix T cross. Okay. it means we should transpose this matrix A and then you are getting T cross. Okay. So, this will show that is f x is equal to, so f x equal to g of T x, which is equal to sigma k equal to 1 to n beta k and e j k. Okay. Now, this implies that T cross E, T cross E, this T cross E, this G equal to F, okay, where beta k is the component form is tau j k alpha j and j is 1 to n. Okay. So, we say if T is represented by, if T is represented by T, then its adjoint operator T cross is represented by the transpose of the T k, transpose of T. This I will explain later on. Let us see. Okay. Thank you. Thanks. Thank you. Okay. I will explain this thing in next class. Okay.